Hi, this is Alex from devstories.eu. PyTorch Fundamentals, Episode 8 of 18. Neural networks only compute numbers, but your real-world data is usually a messy collection of raw image files and text categories. If you write manual loops to convert every single image and label before you begin training, your code will quickly become a brittle, unreadable mess. Data transformations are the mechanism that resolves this, automatically converting your raw data into a model-ready format exactly when it is needed. Data rarely arrives ready for machine learning. You have to manipulate it into a specific tensor format before feeding it into your network. PyTorch handles this cleanly by applying transforms on the fly during the data loading process. When you initialize a dataset, especially in libraries like torchvision, you define these modifications using two specific arguments. You use the transform argument exclusively for your input features, like your raw images. You use the target transform argument exclusively for your labels. It is critical to keep these two separate, as they operate independently on different halves of your data. Let us look at the input features first. Say you have a dataset of raw PIL images. A neural network cannot read a PIL image object directly. To fix this, you pass a built-in torchvision transform called ToTensor into the transform argument. When the dataset loads an image, ToTensor automatically executes two steps. First, it converts the PIL image into a PyTorch float tensor. Second, it scales the pixel intensity values. Raw image pixels generally range from 0 to 255. The ToTensor operation normalizes these values down to a floating point range between 0 and 1. The dataset applies this operation strictly as each image is fetched. That covers inputs, but what about outputs? Your dataset labels might be simple integers representing different categories. For instance, the number 3 might mean a dog. But to calculate loss during training, your model often requires those labels to be one-hot encoded vectors rather than single integers. This means you need an array where all values are 0 except for the index representing the correct class, which is set to 1. To handle custom logic like this, PyTorch provides Lambda transforms. A Lambda transform wraps any user-defined function so it can be applied during data loading. You write a short function that takes your integer label as its input. Inside that function, you create a tensor of zeros matching the total number of categories in your dataset. Then you use an internal PyTorch operation to scatter a value of 1 into the specific index that corresponds to your integer label. You pass this custom function into a Lambda transform, and then assign that to the target transform argument of your dataset. This creates a highly efficient pipeline. A worker thread pulls a single raw record from your disk. The image hits the transform argument, runs through ToTensor, and emerges as a normalized float tensor. Simultaneously, the integer category hits the target transform argument, executes your custom Lambda function, and turns into a one-hot encoded vector. Both pieces are now mathematically formatted and handed directly to your model. The real power of this architecture is separation of concerns. By attaching these data transformations directly to the dataset definition, your actual training loop stays completely blind to the messy reality of your raw files. That's all for this one. Thanks for listening, and keep building.